It's wonderful to have you, Sally. Professor Sally Cripps, everyone, from the University of Sydney. This is our second talk since last month. We had Professor David Steele talking on sampling COVID-19 and what to do about that. And he did mention Bayesian statistics as well, as a lot of work could be done there. I'm not sure if that's in the same ilk as yours. I don't think so, but you're most welcome to speak to us on models and uncertainty in the time of COVID-19. Thank you, Sally.
Well, thank you very much, Brenton. It's a really great pleasure to be talking today. I have a strong connection with Western Australia. I actually went to university there and lived there for a while, and I now have family who live there, although obviously with COVID-19 I haven't seen much of them in the last year, but it's certainly a great pleasure to be asked to speak, so thank you very much. The talk, as Brendan said, is models and uncertainty in the time of COVID. Probably we'll just leave the questions for the end because it's a bit tricky with Zoom. So just to set the scene a bit, I'd like to talk to you about how I became involved in all this stuff and the sort of timeline initially of COVID-19. And as you all will know, so this is a picture of the Megalong Valley, by the way. This is on the west side of the Blue Mountains in New South Wales. And I don't know whether you can see, but that's where I spend a lot of my time. I live in that valley, and it's a very pretty valley. And the reason it's relevant for this particular talk is the following. So as you know, that January the 19th was the first case that we had of COVID-19 in Australia, and incidentally, the first death was actually in WA. A gentleman who was on the Princess, the Diamond Princess, I believe, and they actually docked in Darwin, but the couple became unwell, and that became Australia's first recorded death. And not long after that, I was called up by my son, who was at ANU at the time, and he said, my son actually doesn't call me all that often, so when he called, I said, is everything all right? And he said, I suppose it depends what you mean by all right. And I said, well, Jack, just how are you? And he said, well, he'd sat on a bus next to somebody who'd got confirmed COVID-19, and so he had to go into isolation. And so I drove down and picked him up, and we came to the Megalong Valley, which is a very nice place to be in isolation because you can be outside because there's nobody else around for that, quite a few kilometres. So that's, and in all this isolation, and it really was isolation, there wasn't much internet access, there was no mobile phone coverage, and I spent, except unless you went up to the top of the hill, and so we had to do something. And so I was actually, getting involved. I'm not an epidemiologist, but then I started to think about data, and I was contacted by some old acquaintances, and I just want to run through who these co-authors are. So this was a collaboration that happened while it began in isolation in the Megalong Valley between a whole bunch of Australian and US co-authors. And the Australians are, Roman Marchant is machine learner, Andy Zhu and Vincent Chin, who are both Bayesian statisticians, and all of them work at the University of Sydney. And I was contacted by Ori Rosen, hang on if I can just go back, Ori Rosen, who is an old-time, a long-term co-author from the University of Texas, and a fellow called Martin Tanner, who's at Northwestern University. It says missing in action. Martin's actually not missing in action, but his photo, he won't have a photo of himself on the internet, so I've put down that he's missing in action. So these are Martin and Ori I've worked with in the past quite a bit. And they introduced me to Noel Samia, who's an epidemiologist at Northwestern, and John Ioannidis, who's an epidemiologist at Stanford. And the wonderful thing about working with Australian and the US when you have US co-authors, is you can write papers 24/7 because you go to sleep and then they start working and then you come up and you do it over again. And so we ended up writing 4 papers over this time period, and that's the basis of the talk I'm going to do this evening, but it's very much a team effort between everybody in those 2 countries. So as this talk certainly indicates, we're going to be talking about the uncertainty in COVID-19, and I'd like to sort of introduce a concept which I think is useful when I think about uncertainty, which is the uncertainty pipeline. So if you've got some sort of problem or issue, or you want to have a look at you want to have some informed decision making based on some data, the first thing that you might ask yourself as a statistician is, well, what data exists already? What is around to to use. So which data set, and there are lots of choices now because data is so easily captured and stored, that there is a lot of data which actually it brings into itself a whole heap of uncertainty. And then of course you've got things like sampling bias, measurement error, missing or complete data. All of these are sort of uncertain, or add to the uncertainty pipeline anyway. So you've got your data, and then you start to think about which model. And again, you know, the boom in data science has led to a huge increase in the models and the methods that we have to estimate those models. And so that again is another set of choices, which again actually can influence your conclusions. And so those choices brings in a lot of uncertainty into the conclusions. And in addition, you know, you've got the usual things that you think about, such as, you know, what's the data generating process? What's the likelihood function? Do I want to be non-parametric and go likelihood free? In particular, in these cases, when we were looking at epidemiology, embedding epidemiology models in probabilistic models, you have to start to think about things like, you know, epidemiology models are usually for continuous time. So you've got a finite representation of a continuous time model. You have initial conditions. What was that initial R0? And if you're Bayesian, which I am, and which many of the papers in COVID-19 are, you know, there's obviously the choice of prior. Again, this is what I'm going to be focusing most on tonight, which is the model uncertainty and how that affects our inference. And then that leads to, you know, inference. So you've got your model, you've got inference and prediction, and it doesn't, if you're going to use a frequentist approach, are you going to have to assume something about the distribution of the sample estimates? You're going to have to invoke asymptotic arguments, or at least get finite sample distributions of these sample estimates. And if you're Bayesian, you usually have to solve a large integral, high dimensional integral, and that's usually not available in analytic form. So we often estimate it via simulation, the integral, or you could approximate the posterior by some sort of variational inference. All of these add to uncertainty. And at the end of the day, what we really want is explainable and robust decisions under uncertainty. And it's obviously not simple. It's very difficult, and yet it's something that we really must try to do if we, as a profession, as statisticians, who our business is to quantify uncertainty, is to take data and to get predictions, but to actually estimate what we don't know and quantify it so people can make informed decisions. And what I'm concerned about increasingly as I look at all these models, particularly, and COVID-19 is a great example to illustrate them, is just how much we underestimate that uncertainty. So I suppose I want to be talking about that tonight. And to start it off, I'd like to talk about sort of what are the consequences of not correctly quantifying uncertainty. So, you know, we had back in March, when these papers were originally written, there was the governor of New York, a guy called Andrew Cuomo, and he said on March 24th, I don't have a crystal ball, everybody's entitled to their own opinion, but I don't operate on opinions, I operate on facts, on data, on numbers, and on predictions. So on March 24th, Andrew Cuomo was a sort of a paid up data scientist, a card-carrying member of the, you know, the Brotherhood of Big Data. He actually believed that by using data analytics, that actually data analytics was the crystal ball. Here I operate on facts, on data, on numbers and projections. So he went from this position on March 24th to this position on May 25th, so 2 months later. Now, as you can see, now people can speculate, people can guess. I think next week, 2 weeks, I think a month, I'm out of that business because we all failed. You know, he goes on to say, you know, here's my prediction model. They were wrong. They were all wrong. So we've gone and from somebody willing to take on predictions from models and make decisions on them to being totally disillusioned. And I think that this is the danger that we get into when we don't correctly estimate uncertainty, is that the public lose faith in, you know, policy decisions based on statistical modelling. And that's a sort of a theme of what I want to talk about. But in order to get there, let's have a look at what sort of uncertainties there are around, what sort of model uncertainties, and how we might think about evaluating models relative to one and another. So the first type of uncertainty, you know, that I put up was this data uncertainty. And I'm just going to talk very briefly about that because it is mainly about model uncertainty. But when we first started to have a look at these models, and we had to, you know, get the ground truth, and which is most of these models chose death very sensibly as their data to anchor on rather than cases, because the deaths are something that are sort of usually, you know, recorded, they're accurate, and you know, they may be a little underreported, but not as much as cases. So we looked at the data, and it turned out that even just for one state, there were many models, and there were sort of 5 versions that you could readily find of the ground truth, each of the models using a different version of ground truth to train their data. And these were wildly, although they had this sort of trend, they were very different, you know, on their day-to-day fluctuations. And these people were making daily predictions and 95% prediction intervals. There was this red line here is the Johns Hopkins University data. The smoothed green line was the New York Times data. There was COVID tracking data. The Johns Hopkins not only had its raw data, but it had something called the Johns Hopkins time series, which you can see at one point, you know, we had people resurrecting because there was, you know, negative deaths. So I suppose I want to use this as to say that although I'm going to talk about evaluating models, you know, it's pretty hard to develop a really good model when you've got such different ground truths of the data to anchor your model predictions with. Okay. So now I'm going to talk about model uncertainty, having said that about the data. But I did want to start by saying, I think, you know, it's just absolutely fantastic that researchers make their code and data publicly available. They really are to be congratulated. And it would be a shame if talks like this meant that people didn't, you know, put their data and models up available for everybody. I think what we need is this transparency. And so, although I'm going to now evaluate the models, I want to actually, you know, acknowledge the generosity and the openness of those people who do actually make their code and data publicly available. I'm going to split models into predictive models and inferential models, and it's a bit of an artificial distinction in my opinion, because predictive models are predicting to predict into the future. Inferential models are to make inference about some quantity of interest. And of course, you know, predictive models are just inferential models when the quantity of interest is what happens in the future. So it's a bit of it is an artificial distinction, but I think it's useful in this case because they were used in different contexts by policymakers. So I'm going to start out by talking about predictive models and then talk about inferential models. So the first model that sort of hit the big time was a model by the Institute of Health Metrics and Evaluation, the IHME model. It was at the University of Washington, and they came out with daily predictions for states across the US, as well as for the US as a whole. And in addition to those daily predictions, they had 95% prediction intervals. And so if you think about how you want to estimate these models, are they accurately estimating? Are they getting good point estimates? But also, how good are they at accurately estimating uncertainty? So these models, this particular model was used in the White House. It was quoted quite a lot in the press, and it was very informative in the US in the early days of policymaking. When we started to look at it, we looked at it as if, you know, it was making a prediction. For example, here, this is March the 30th. These numbers here relate to 1 day ahead predictions. So this was a prediction for March the 30th based on March the 29th. So 1 day ahead, we're not talking about long-term predictions, but merely predicting what was going to happen the next day. And in looking at how well they performed, the thing that struck us the most that was they had these 95% prediction intervals, but for that day, you know, only 29% of the data fell within the 95% prediction intervals. For the next day, so this is March 31st, we move on. 1 day, they make another prediction on March 30th. For that day, 33% of the data were in the 95% prediction interval, only 25% the following day, and 49%, so getting slightly better, by April the 2nd. So they clearly weren't great predictions, even though they were being used at this point by policymakers. And in fairness to the IHME crowd, they recognised this and they updated their models. And they updated them on April the 2nd. And now we see that this coverage is getting much better. It's not 95%, but 73 is a lot better than 27. And we're getting up towards 92% by April the 17th. Now, of course, one way to get 100% coverage is to just have hugely wide prediction intervals. So you may not have actually improved the model in terms of the point estimates or its usefulness. You've just increased the coverage, and in fact that's what happened. So I have here a estimate of a model for the number of deaths in New Jersey on a daily basis. The blue line is the model that was made on the 29th of March. Here it is here, this blue line, and you can see this very narrow band was its confidence, or not confidence, prediction interval. And the black line is the actual data, and you can see that the actual data was departing from the blue prediction, and they very sensibly corrected for it. But then if you look at these are now the predictions going forward. If you look at the confident or the prediction intervals for daily deaths, they are, they range from, sort of close to 0 to 2,500. Now, you really don't need a fancy statistical model to say that you think that the data is going to fall somewhere between 0 and 2,500. So the usefulness of this model to form policy decisions is very, very questionable. So moving on to other metrics. So I'm now going to focus in on the previous slides were from our first paper, which was called Learning as We Go. And these, then we had a look at how, what was happening in New York. New York was one of the early disasters, and you saw that we had that quote from the governor of New York. So we thought, okay, so what were the models saying at about this point in time? So we have 4 models here. The Institute of Health Metrics is the only totally data-driven model. The others have some combination of what's called an SRI model, which is an epidemiological model, which I'm sure you're aware of, and maybe some curve fitting in it as well as that. But the IHME model is the only totally data-driven one. Now, just want to explain these graphs for a time being. The black line is their ground truth. So, and different models, as I explained, had different ground truths. So these are the ground truth for the LANL, the Los Alamos National Laboratory one. This is the ground truth for what was called YYG. A guy at MIT just did this all by himself. The IHME actually got 400 million from Bill Gates. So, actually YYG was doing a pretty good job on his own. And this is the University of Texas. Now, so they're the black or the grey lines are the ground truth. The reason that's gone from black to grey here is because University of Texas shifted from using New York Times as its ground truth to the John Hopkins time series as the ground truth. These curves represent the forecasts, and they're color-coded for when the forecasts were made. So at the hot end of the spectrum, the reds, if you think Roy G. Biv, so these were made early on in the piece, these projections, and the ones that are mauve were made later on in the piece, and you can see them coming in over time. So these were the models that they were projecting, and this is the ground truth where these projections relate to different points in time. This was from the second paper. This is one that's actually already been published. This was at the European Journal of Epidemiology. This has been published. And so these are the 4 models. The paper was called A Case in Model Failure. You can sort of know the punchline by the title, I suppose. And so then we went to look at, so how do you compare, we wanted to know whether one model was better than another. And, there are lots of ways of doing this. And one way is to have a look at the mean absolute percentage error or the mean absolute maximum error. And I suppose here we compared each model I just sort of want to focus on this bottom panel here, because this is for the mean absolute percentage error. It really only makes sense to compare each one only to its training ground truth. And you can see on that basis, obviously a lower value is better, and each color represents a different model. So we've got the IHME with the orange, the LANL is the green, University of Texas is the blue, and the purple is the YYG. And you can see that the IHME model is doing pretty well. By comparison, here is the formula. So basically we took, so this point here, for example, was using a forecast way back here. We averaged over the difference between that forecast and the actual deaths to get this point, and then moving forward there was another forecast, and then we averaged over all of that, and so on and so forth. And as I said, this IHME model is doing the best, but that's because it's using the nice smoothed New York Times data as its ground truth, as opposed to these people here. So when you evaluate this compared to its ground truth, you're going to get, it's a much easier task to estimate a smoothed than a jagged ground truth. So then we had a look at all the models based on if using New York Times as the ground truth, and you can see they're all pretty similar. In fact, the point of this graph was to say there's really nothing much between them. They all did a pretty poor job of estimating actually the daily deaths in New York at around that time. So if we move on to the accuracy of the uncertainty forecasts, again here on this top row is IHME. So what these are the 95% prediction intervals. The red dots are the actual, the red dots are the actual data, and the black dots represent the mean prediction for that point. And you can see that the IHME model, you can't see the prediction intervals there because they were so tiny by comparison to these wide prediction intervals. And this was trying to get at, is there some model that actually uncovers or does the best job at getting the uncertainty estimates, which was our focus. And if you look down through them, the LANL model here is the best model in getting the uncertainty estimates. It does actually have quite a good job, but unfortunately this model did not come into being until mid to late April. So it was unavailable for people making decisions in New York at this particular point in time. Here's the University of Texas model. It was basically underestimating uncertainty. And here's the YYG model. It actually did a pretty good job, but because it was training on this incredibly jagged ground truth, it made it a lot harder for itself. So we came to the conclusion that actually most of the models were pretty much rubbish for predicting daily deaths. They were also, at least one of them, were predicting ICU, hospital ICU utilization. And these are the predictions for the number of hospital beds that were needed in New York. Now, the black line is the prediction, the grey is the uncertainty around that prediction, the blue is the capacity, and the red is the actual. So as this is the 25th of March, this is the 25th of March, this is 29th, and so on and so forth. You can see that there were these huge over predictions here. They were getting slightly better, but still even, even on the 1st of April, they were still, when we knew a little bit more about what the hospital usage were, they were still widely over predicting, and it wasn't until much later on in the piece that they got actually any sort of sense of predicting what was actually going to happen in these hospital bed utilizations. And when we presented this once, I presented it once to a group of epidemiologists at Stanford, and they said, well, does it really matter? I mean, they predicted it was going up and it was coming down, and it did go up and it did come down. And the answer to that, well, yeah, it does matter, because on the basis of these graphs, on March 25th, 4,500 COVID positive patients were discharged from hospitals to nursing homes in anticipation of the need for hospital beds. Nursing homes are full of highly vulnerable people, and in New York alone, over 5,800 deaths occurred in nursing homes. So these models were being used for policy decisions, which had, in this case, absolutely tragic consequences. So at the end of the paper, we came up and, what were our big takeaways? Well, we need decent data. I mean, you can't really do much without decent data. So we need serious thought and investment. And the same is true for Australia. I think we've missed a big opportunity actually to start been collecting very good data by not investing in that in the beginning. Also, that models need to be subject to real-time performance before their results are provided to policymakers and public health officials. That is, when you look at big decisions that are going to affect the health of millions in the same way as you have trials for vaccines, we need to have some control around what models are going to be used, and they've got to be subject to performance tests that are specified in advance, as one would do in a clinic, in a well-run clinical trial. We don't just take possible vaccines off the shelf, and neither should we take possible models off the shelf if those output of those models is going to be to make decisions which affect the life of billions. Right, now I would like to turn my attention to the second class of models, which are inferential models. And in particular, a lot of the inferential models try to answer the question which non-pharmaceutical interventions are the best. Nobody wants to be in lockdown, but we want to have as much freedom as possible, but at the same time contain COVID-19. And until we get a vaccine, non-pharmaceutical interventions such as social distancing, washing your hands, wearing a mask, lockdown is a version of an NPI, event ban, all these things, they are our only means of stopping the spread of COVID-19. So it is a very big and real question. This problem was addressed by the Imperial College, their COVID-19 Taskforce models, which we also adapted, and I'll talk about what we did with them later on. But for now, I'll give you a sort of a rundown on the way that these sort of SRI type models work, so that you understand how they came to the conclusions that they came to. So they wanted to build a model that would somehow get at what was the impact of non-pharmaceutical interventions. How are they are some better than others? And if so, by how much? It is well known that, by definition, infectious diseases spread because of contact with other people. If you don't contact anybody, you're not going to spread the disease. So they work by reducing contact. That's their goal. And there's no doubt that all the non-pharmaceutical interventions do that to some degree. And the question is by how much, and how much does that reduce the rate of spread, and at what cost? Unfortunately, isolating people is the way to go to stop infectious diseases. The reverse is true for mental health conditions. People being isolated is bad for mental health. So, there's some balance between the two that needs to be made. Anyway, here's an infected person, and the model often the models look a bit like this. This is a distribution here of the time it takes for an infected person to infect a new person. So this is typically a gamma distribution, and this is estimated from what they've observed in the past. And the number of people who are infected at at time t, and the subscript M here refers to country, is basically a sum of the people that were infected in the past times the time that it took them to infect a new person, which is this G function, times this RTM. And this is the critical thing. This is what's called the effective reproduction rate. This is that, how many people a single person will reinfect. Okay, so the model goes that it goes to there. A new person gets infected. There's a distribution over the time until they show symptoms, and there are assumptions made about that. And this is again, that's a gamma distribution. There is a time from symptoms until death, if death occurs. Now, and they model death, as it often is, as a negative. This is a negative binomial with a mean and a variance. And this was a Bayesian hierarchical model. It was different for different countries, but it was a random effects model essentially. And so that's how they modeled. And so their likelihood function, the data that they used was death data. It wasn't cases reported, it was death data. And as I said in the beginning, the key is to see how much non-pharmaceutical interventions will shift this, and we'll see the impact of a reduction in this in the reduction in deaths. So that's the key, is to get this down. So that's what the a lot of the work centers around, trying to estimate that in an effective fashion. Okay. So they came out in June. This is Imperial. They came out in June and they said that we find that across 11 countries since the beginning of the epidemic, we've saved $3.1 million due to interventions, and lockdown has been responsible for an 81% reduction in RT, that effective reproduction rate. And this was the model that they used here for RT. So what you can see is you start off from some R0. This had a prior distribution over this R0. And then this is just a piecewise function. The exponent here is obviously to keep things positive, because we're talking about, this is RT is a number that goes anywhere between 0 and a very large number, I suppose. It could typically, we want RT. If RT is below 1, I should have pointed out, the disease dies down. If RT is above 1, you get to, it keeps growing until such times as enough people are infected in the population that there are no more to infect. And then, of course, it starts dropping. So they modeled this RT as effectively as a stepwise function, where they had a dummy variable that just said if non-pharmaceutical intervention K, and I've listed them over here: lockdown, event ban, school closure, self-isolation, self-distancing. So if non-pharmaceutical intervention K at time T in country M was in place, then that's dummy variable equals 1, otherwise it equals 0. So it was deliberately simple because they wanted to try and get at the effect of these NPIs. But such a model, the only way that RT can possibly change is via an NPI. I mean, we know that RT will change over the course of an epidemic. Mainly often because, it gets, populations are not homogeneous. So it'll go into one population and you'll see a number of, the RT will be high and it'll start to come down as more and more people get infected until it goes into a different sort of population, whether those different populations are based on locations or age or whatever. So non-homogeneous populations will actually change RT, but this assumed everything was the same. And as I said, and this is their example in the UK, there are many countries, and they said, this is a classic example, they said, therefore, lockdown had this huge impact. Now, there are a lot of things wrong with this, right? So, if you've got RT that's coming down anyway, then the last intervention is going to be the one that you think picks up all the reduction in the RT, because you've allowed no other intervention to happen after then, and no other way for this thing to decrease. So there's quite a bit that's wrong with this. And we then sort of were thinking about how else we could do it. And we were, around mobility data. And we came across actually a paper also by them, which actually did a similar thing, but for the US. So they had one model, which was this model for modeling RT for the UK. And this model was used for states in the US. So basically this X here, and I'll show you some pictures of mobility indexes in a while. This X is the mobility at time T in our case, it was in a country. They had other bits and pieces in this model too. And this Epsilon here, this is an error. This is a sort of also putting in a bit of a statistical model. This was a weekly AR2 process that they put in to sort of model how it was evolving over time. Here's the XT, is the Google Mobility Index. And this is this function here. It's 2 times this, you know, the logit function. I'm not sure why they used a 2, but we wanted to compare with what they did. So we got their model, and we got from, you know, and then we got the European data and applied this model to the European data. And here is the model for the UK. You can see it's exactly the same death data, you know, so same death data here. These data are exactly the same. I might want to point out to you, actually, I didn't go through this all that, I went through this a bit briefly. This first panel is the number of infections, and you can see just how much underreporting there is. The pink is the actual, and this is the projected. This is the estimated, and so if I can go back. And again here, you know, so this is a model, but, you know, that was anchored at death, using death as a data, so we would expect it to fit the deaths well. And obviously RT is never something we observe, it's something we infer from the data. But you can see here's one function of RT, and that's the projections from this model to give you these projections to fit this data. And you see you get a very similar fit for this model, but if you look at the evolution of RT, it's quite different. And in fact, if you have a look at when lockdown was introduced, it was introduced here effectively when the RT was already at 1, so it had minimal impact for the UK based on this model. So very, very different inference for policymakers about what do you do to reduce RT the most. One is saying, well, this one, if I look at this, maybe social distancing. I mean, I'll come back to how we might evaluate these, but it's a very different picture from the first one. The RMSE for this model is not quite as good as the RMSE from here, so you could argue that this is a better fit to the data. Either way, if you've got 2 models that are giving you vastly different inferences and advice to policymakers, it should make you think about A, reporting the results of both, and B, thinking about how you might figure out which one is a better model. And that's what we did. So before I go on to how we did that, I just want to have a look at, so what does this mobility data look like? This is from Google. It has different measures of mobility based on mobile phone data. And here, the first dotted line is when lockdown was introduced, and the second dotted line was when it was lifted. And I suppose what you can see, it's probably more clear in the United Kingdom than anywhere else, is that, you know, for whatever reason, whether it was from centrally imposed interventions, whether they were lockdown, social distancing, or whether it was from people acting individually by themselves, that there was a big drop in mobility prior to lockdown. And then I think, you know, maybe one explanation, that's not the only explanation, one explanation is that, you know, this was a very uncertain and scary time. People were very worried about this new epidemic, and they stayed at home. And as people got a little bit more confident over time, you know, the mobility starts to come back. You can see that the lifting of lockdown doesn't seem to reduce this recovery of mobility at all in almost any of the countries, except perhaps Italy. Seems that the Italians actually did stay in lockdown when they were in lockdown. But so there are many explanations, and that was one I just gave, but it is interesting to look at how much lockdown did increase mobility. Of course, mobility is not exactly the same as no contact, but it is a consequence of you know, reducing individuals' contact with each other. So then we thought, well, what about if we take this data out a bit further and see whether or not that sheds light on anything? And then we wanted to also allow for the fact that the imposition of an NPI such as lockdown, may be different in magnitude. The impact of an imposition may be different in magnitude than lifting it. So that's why you've got this I for imposition and L for lifting. So these are different dummy variables. And if we look at the data, this is for model 1. That is for this model here at the top. This is for model 2 down the bottom. Don't pay too much attention to these Zs. Actually, that's a typo. That should be the same equation that was on the previous slide. My apologies. And this is the United Kingdom. So again, exactly the same data. This is the difference in RT. These are, I've just blown up this region here so you can see it. And you can see that once we start to extend it, you know, the inference or the picture for model 2 doesn't change all that much from the original picture that you saw on the previous slide. So the additional data doesn't really affect things. And you can see that the additional data for here does affect things. We start to see that maybe there were other interventions, this was actually school closure, that may have had as big an impact on the RT as lockdown, just showing you that these are different ways of, you know, viewing the trajectories and what they mean for policymakers. These are the graphs for various different countries. There's Austria, this is model 1, model 2, Belgium, model 1, model 2, and so on and so forth, Denmark, France. And you can see a pretty consistent picture emerging, which is that model 1 looks like there's a lot, lockdown had a big impact. Model 2 says not quite so much. These are Germany, Italy, Norway, and Spain, and Sweden and Switzerland. So which one? I mean, which one should they use? I mean, should model 1, model 2? And of course, we believe it's important to really make sure that they're aware of both, particularly if you've come up with them yourself, and to make sure that they're aware of both and to somehow compare them. So here I'm just doing a very basic thing, which is this is just the root mean squared error. This is the shorter time period. This is the longer time period. For the shorter time period, we had that the root mean squared error was better for model 2 in 9 out of the 11 cases. In the longer time period, it was better. Model 2 was smaller. In other words, it fitted the data better than model 1 in 11 out of the 14 cases. If I wanted to do something really rudimentary, I could calculate a p-value, you know, say, you know, it's the number, you know, if the probabilities were the same so that I would expect they're both as good as each other, you know, I could count these sort of p-values. That would be sort of some very rudimentary measure, but, you know, something that anybody could really do. Or we could do something a little more sophisticated with information criteria. And the information criteria, these are the, I've listed the references for these and the justifications for them. I suppose one of the justifications here was that it's actually, you can use the output of the MCMC to calculate these, and it's not computationally intensive. In some sense, what you'd really, I suppose, like to do is something like cross-validation, but that is very computationally intensive. It doesn't come for free from the MCMC scheme, and we wanted to get this paper out. So we used these these two measures of information criteria. These both measures have the same structure, which is you get the log posterior, the estimates of the log pointwise posterior predicted density, the LPPD, and you actually penalize it by the number of parameters or the effective number of parameters, because it's very hard to know what the number of parameters are in a hierarchical Bayesian model. So there are ways of estimating these things. Here are the effective number of parameters that are estimated. And so these are the information criteria here lower, you know, so this, so for model 2, for both time periods across all possible, or across 3 possible information criteria is the better model of the two. So this is pretty convincing evidence that model 2 it performs better than model 1. It's not to say model 2 is correct, because as we know, all models are wrong, but it is better than model 1. So if you, based on that basis. Then the Imperial College came back and said, well, you should put them together. You should have both the impact of the NPIs together with the mobility. And of course, you can do. we found still that the biggest impact was as a result of mobility, but that the event ban and lockdown in this instance had similar effects. So they initially did this too, except they only put lockdown in there. They didn't put all the other non-pharmaceutical interventions, and they said that lockdown still had a huge effect. We thought it was more in the spirit of the original paper to include all the other NPIs in the analysis, and to show that lockdown and event ban have similar effects. And it's just a very different from if you're sitting in there, you're thinking from a policy point of view, this is a very different world to, assuming that 80%, that all the reduction in RT was attributable to lockdown. Lockdown and event ban are both NPIs. Event ban doesn't have, it has obviously adverse consequences, but nothing like the total lockdown has. And if you, it would be something that you would try before you would go to total lockdown, if you believe this story. I'm cautious about putting this up because I do want to say that we've done it just because it was in a report, a review by Imperial. I want to say that they're really so confounded. I wonder at the, how accurate this model actually is, because NPIs reduce the effective reproduction rate by reducing contact amongst individuals, and mobility is an indirect measure of that. And it does make inference, untangling what's due to mobility and what's due to this very, very difficult. Oh, that's right. So before I sum up, I just thought you might all like to know, well, particularly if you've got relatives in Victoria. So here's Victoria, here's stage 3 lockdown. So this is at model 2, this is applied to the Australian data. So it would seem that, that it was coming up. So it was sort of reaching a plateau, but it clearly had a very large impact on the effective reproduction rate. It was heading up, to 2.5 to 3, which is very high indeed, in late June. And that stage 3 lockdown certainly reduced the effective reproduction rate substantially. Whether or not, they introduced stage 4, so because they felt that stage 3 wasn't getting there fast enough. If I look at this slope here and I look at this slope here, I would say that I think it probably was getting there fast enough. I don't think we've seen a change in that slope, but it's early, this is just one model, and there could be many other explanations or many other models that would have a look at what's actually the impact of various measures that have been used in Victoria. In New South Wales, I just want to point out that it looks like that these are sort of similar graphs, but these are daily deaths in Victoria. This goes from 0 to 50, whereas this goes from 0 to 5. So they are quite different situations. This is New South Wales. We're hovering at 1. We're keeping a little bit under there, and I hope very much that everybody keeps up all the social distancing and whatever else that we can do that doesn't require, the really negative impact of lockdown, but at the same time keeps the COVID-19, the effective reproduction rate down at below 1, so that eventually, we will get out of this with a bit of luck. And I think that the New South Wales Premier has done a great job at doing just that. Okay, so what are the takeaways from this? We're getting very different trajectories of this RT, but it's giving rise to, visually similar data. Even though we've shown that model 2 is better statistically fitting, model 1 is not implausible either. So this is a concern. If these different trajectories yield different interest regarding the effectiveness on an NPI, then the more information is needed, really, and we need to alert policymakers that there are different models that come to different conclusions, because otherwise we are ignoring model uncertainty. So if I can now come back to the, what we started with, which was our uncertainty pipeline. Currently, I know we try to capture the uncertainty here, but we don't have a systematic approach to doing it. And I think that that's exactly what we need to do as statisticians, is have principled pathways which we do actually address model uncertainty. When it doesn't really matter whether you decide to be frequentist or Bayesian, both p-values and posterior distributions on parameters of a given model. I'm not now talking about theta being a model, which of course it can be, but I'm now talking about given a model. Both of those quantities really only are, are talking about the uncertainty with inference and prediction. And, if we really want to get these explainable and robust decisions under uncertainty, there's another huge area of uncertainty that I think needs to be addressed that I haven't talked about, and I'm not going to talk about other than to briefly mention it, which is what about uncertainty in our utility or objective functions when we make decisions. So one way of studying decision making, or what's the right decision, is to say, you're going to average over all possible future scenarios and choose that decision which maximizes utility or some objective function. And this brings me to, what I think one of the key issues in all of this COVID-19 has taught me is, there are many possible objective functions, and they also bring in uncertainty. One objective function could be to minimize COVID cases. So we're just interested in minimizing COVID cases. A more sensible objective function would be to minimize COVID deaths and hospitalizations. And you could argue, of course, that minimizing this will minimize that, and that is also true. However, the focus should really be on minimizing, protecting the vulnerable and the unwell more than I think that we did do initially, and I think we're getting better at doing that now. We could also want to maximize public health outcomes. COVID, deaths due to COVID and hospitalizations due to COVID are one adverse public outcome, which we certainly want to minimize, but we actually want to maximize overall public health outcomes, which includes mental health, which includes things like domestic violence, which have increased over the pandemic. So we want to maximize public health outcomes. I'm not going to talk about economic outcomes because I'm not an economist, whereas I do quite a bit of work in mental health. But we actually also might want to maximize health and economic outcomes. So, when we think about why is it that we focus in on minimizing COVID cases, I imagine it's because it's measurable and people like things. When I go to the gym, and I used to go to the gym, and I like it because I can run on the machine, I can see the calories tick over. And I think that's a bit of the same as, when we want to actually we want to really maximize public health outcomes. And it's easier to focus in on one thing. It's sort of mission clarity, but I think it misses the larger picture. And most importantly, if we were to choose a different objective function, how would our decisions change in response to changes in objective function? So, concluding thoughts, I want to say, again, a big thank you to researchers who make their code and data publicly available. I want to say that big data does not necessarily mean a reduction in uncertainty. And I think I don't know that I think the stats community is better than the data science community at large. I hope they're, but I do think a bit more humility from the data science community is needed. We should underpromise and over-deliver, not the reverse. And I think that at the beginning of the pandemic, the data science community, certainly in the US, were doing the reverse. We should invest in quality data collection. We need to models need to be tested if they're going to be used to inform policy making. If the inference of the effectiveness of an intervention is not robust to model specification, then we need to find out why. And I just want to end with the latter part of this paper was based on a work that's currently under review at Nature. It's called A Tale of Three Models. We conclude with the purpose of this paper is to demonstrate that there's substantial model uncertainty which is ignored, and that inference around the effectiveness of NPIs is highly model dependent. Failing to report this uncertainty to those who make policy decisions, and this is my big concern, will ultimately undermine the public's trust in the value of decisions based on statistical modelling. In attempting to answer the question which results should be used to guide policy making in lifting restrictions, we must be absolutely transparent about what we don't know. Thank you.